Okay. Well, thank you for the invitation. It's a pleasure to be here. So everything I'm discussing today is joint with Ahmad Issa, who's a grad student at UT Austin. So I'm not sure what your sort of favorite 3 and 4 manifold fact is, but my favorite is that, well, the Poincare homology sphere sort of bounds a topological homology ball. That's due to Friedman, but does not bound a smooth homology ball. So yep, I can write bigger, and I will. So does bigger chalk mean bigger writing? Okay. We'll try this. Okay. And, well, how can you get at this fact? Well, there are, lots of proofs. Okay, I'm sorry, I'm going to go back to the small chalk. There are lots of proofs of this, so, more or less any reasonable sort of 4-dimensional theorem or theory will spit out this fact. You can use Rocklin's theorem. Haygaard-Fleur's pretty popular around here. You can use the D invariant from that. There are sort of custom Seifert fibered space sort of invariants like the Neumann and Zagier invariant, the R-invariant, which will give you this. But I'm a sort of a Donaldson's theorem enthusiast, so let's prove this second statement using Donaldson. So what would the Donaldson theorem proof be? Well, the key observation, well, I guess to most of the possible ways you could prove this, is that, well, we can choose an orientation on P, and we're going to assume that we've oriented the I'm going to call this P. Orient the Poincare homology sphere so that it bounds, well, positive definite E8 plumbing. So that's a 4-manifold whose intersection form is given according to this graph. So what that means is for each vertex you have a generator. Their self pairing is given by, well, there's 2 given by the number associated on each vertex, and then these vertices pair with 0 if there's no edge between them, and -1 if there is an edge between them. Okay, and so I guess I'll call this E8 plumbing X. And then what do you observe? Well, you observe that if P were the boundary of WA smooth integer homology ball, then you could form a closed smooth 4 manifold. And then at this point, Donaldson's theorem comes in and says, well, hence its intersection form is diagonalizable. Okay, and in particular then, well, the inclusion of sort of X into this closed manifold would give you an embedding of the E8 lattice into, well, I guess in this case I'm talking about a homology ball, so into Z8, but we might as well just call this N for some N. Okay, and well, this is our contradiction because this is impossible. And now, if you're a sophisticated individual, unlike me, you would observe that every unimodular sublattice of a diagonal lattice is itself diagonal, and then point out that, well, E8's, not diagonal. It, for example, you can observe that it's even, or at an even more meta level, you can observe that, well, we've given it a special name, 8, so it can't be diagonal, because otherwise we'd just be calling it Z, the N for the relevant N. So there are two proofs for you, but I'm not sophisticated enough for either of those, so I'm going to tell you how I would do this. And, well, the way I would do it is, well, just to do it, right? So if we have an embedding of E8 into Z to the N, we can write, we can find vectors in Z to the N which pair, as according to this graph. So let's try and do that. So okay, and well, there aren't many vectors of norm 2 in a diagonal lattice. They all sort of, well, I'm just going to say, I'm going to write, EI is a, EI is a orthonormal basis for Z to the N. And well, there's only really up to sort of relabeling enzymes, we can assume that, well, our first vector of norm 2 looks like this. And the way I'm going to try and, proceed here is we've got this sort of chain of 7 2s across the top. I'm going to do that first, and then I'll come back to this, well, what will turn out to be troublesome little fellow dangling off there. So we don't really have much choice for the first one. Or it turns out, if we want the second one to pair -1 with this, we're sort of forced to take something that looks like this. And now, well, for the third one, if we wanted to, we could try this. But, well, at this point, we'd run into trouble because these two are congruent mod 2, and then there would be no way to introduce a fourth thing which pairs 1 with this and 0 with this. So this one's out. So our third one has to look like this. And then continuing in this way, we sort of find that we have no more choices. So find that the only way we can sort of embed this chain of 2s is to produce the only way we can embed our chain of 2s is to do something like this. And now we need to embed this, this final 2. And well, this needs to pair 0 with everything except this sort of single 2 here. And now when you try and do this, well, you find that you've snookered yourself. If you choose to take E6 in here, well, now we need to have we need to introduce some other thing to make this pair 0 with this, and well, you'd have to take, say, E7, but now it pairs with this, and now, we've got a thing of norm 2, and we can't add anything else to it, so, now we're stuck. A similar argument says, well, say if we tried to include E5, then you'd sort of be forced to try and go the other way, and you'd, again, run into the same problem. Okay, so I like this proof, and it's sort of natural to think, well, what else can you generalize? What other manifolds can you generalize this to? And well, the point was that we had this, plumbing, definite plumbing, and well, there are lots of other manifolds with definite plumbings, the Seifert fibered spaces. So, can we generalize this? So, okay. And obviously, the answer is yes. But before I explain how you might do this, let's set up some notation. So, I'm going to let, well, say, Y be the Seifert fibered space. Let Y be. And this is going to be the Seifert fibered space, which you can obtain by surgery along this diagram here. If you don't know what a Seifert fibered space is, you can, for the purpose of this talk, you can take this as a definition, although that might make this all seem a little bit pointless because I pulled a random surgery diagram up and started working with it, but never mind. So, for me, this is a Seifert fibered space over base orbifold S2, and what I'm going to discuss can be generalized to other orientable base, for any other orientable base surface, there's a sort of a natural generalization of what I'm going to discuss, but I'm just going to stick to S2 for today. Okay, and I'm going to take the conventions, so I'm going to normalize these invariants. There's a lot of redundancy here. I'm going to take the convention that, well, these are all going to be at least 1, and I'm going to sort of, by changing orientation if I want, I'm going to assume that well, quantity epsilon y, which is defined to be E minus E minus the particles of these is positive. Okay, and it's this assumption here is giving us the positive definite plumbing. Okay. Okay, but where is the plumbing coming from? Well, I guess I can be explicit, and well, if you want, you can do a little bit of surgery calculus. Convert sort of each of these fractional surgeries into integer surgeries. I've already used n, haven't I? Let's call this k. Let's use L. A1n all the way down to, well, ALN. Okay, and then, well, we convert to integer surgeries. And well, this describes a four-manifold a four-manifold X, and the intersection form is, well, just given by this graph here. Okay. And as well, the relationship between these integers and these surgery coefficients are given by continued fractions. So where this sort of minus continued fraction is shorthand for the Hertzsprung-Young continued fraction you get by sort of putting minus signs in your continued fraction. And we always have such a continued fraction where these coefficients are at least 2. Okay. And then, well, the condition that I asserted earlier that I want epsilon of y to be greater than 0 is enough to guarantee that, well, x is positive definite. So, one way you can see this is that each of these arms gives you sort of a bunch of disjoint linear chains, so that gives you a sort of a positive definite subspace of your intersection form in all but sort of, one dimension. And then when you sort of compute the overall determinant, you sort of naturally find this quantity crops up, and then this being positive gives you sort of positive definiteness. And the other useful fact that I should mention at this point is that if you want to compute the order of the homology of y, then this is simply, well, this is the way in which the determinant naturally, the determinant of this, the matrix corresponding to this naturally crops up. This is simply this quantity here. Okay, and so, well, now we've got, a bunch of spaces with intersection forms that sort of look like this. And so, what can we do with these? Well, we can try and run, well, we can ask for which of these things does this proof work. And so notice that actually I've shown here slightly more than the fact that the Poincare homology sphere doesn't bound a integer homology ball. What I've actually shown is that with this orientation it can't bound any negative definite manifold. And, well, okay. And well, to which other Seifert fiber spaces can are similar sort of statements true? Well, in 1985, I'm not the first person to think about this. Neumann and Zagier showed that, well, if Y is a integer homology sphere, a Seifert fibered integer homology sphere, then Y bounds a okay, from now on I'm talking about I'm working with everything smooth, then then E is equal to 1. So I'm using this, this notation and these conventions up here. They showed that simply the fact that we have this plumbing with a 2 on the center shows that the integer, the Poincare homology small sphere doesn't bound an integer homology ball. And then, well, how did they prove this? Well, I've been talking about Donaldson's theorem for quite a bit now, so you might think that the answer is going to be Donaldson's theorem. Well, it isn't. They used sort of Fintushel and Stern's R-invariant. But they did ask the following. Can you get the same from Donaldson's theorem? And I want to tell you that the answer to that question is yes. And in fact, you can get somewhat more from Donaldson's theorem. So the answer is yes. Yes, it's pinned down by the assumption that these numbers are greater than 1. So the redundancy sort of comes up to sort of doing Rolfing twists on each of these components, which changes the denominator by sort of pi. So there's a unique one of those, and then, for example, the homology nails down everything else. Yes, and more. Okay. And this is what we came up with. So, well, before I sort of tell you our generalization of this, I'll tell you the sort of general criterion we got from Donaldson's theorem. So if Y is a Seifert fibered space, the form we've been discussing with the conventions we've been discussing. Okay, so oriented to bound this positive plumbing. And if Y bounds, well, smooth negative definite manifold, say then, well, we get the following sort of condition on these invariants. So what is this? There is a partition of there's a partition of these Seifert invariants. So let's just write this. Well, into at most E classes, the E sets, which we'll call C1 up to CE, where I guess I'll take the convention that if it's less than E, I'll just take some of these to be empty and everything will be fine. And then what's the condition? Well, the condition is that for each of these subsets, when you add up all of the invariants in that class, well, you get at most 1. Okay? And so, one way you can think about this is you can think about it as a refinement of the condition that epsilon y is greater than 0. You notice that if you if you add up all of these, then you simply recover, well, the condition that epsilon y is, greater than or equal to 0, and, well, I guess I'm sort of assuming we're dealing with a rational homology sphere here, so then you find that this, epsilon y can't be 0. So, in that sense, this is a refinement of this condition. And then the proof is idea is, well, as has been said, the proof goes via Donaldson's theorem, and what you do is you take, this 4-manifold X here, you glue it to your smooth negative definite manifold with its orientation reversed, and you get something closed. Then you get an embedding of this intersection form into a diagonal lattice, and then, well, I won't tell you the details, but I will tell you, well, where do these classes come from? And, well, we have this embedding here, so we can look at the so the thing of, weight E in this graph here, okay, well, in a diagonal lattice, and involves, right, it has, this maps to a vector of norm E, so this involves at most, so, well, so then how do you come up with this partition? Well, you look at each of these orthonormal basis vectors, and then you group together, well, notice that we have these arms here, and the first vertex on each arm pairs with the central vertex, so it must have a non-zero coefficient sort of matching up with at least one of these E basis vectors. So for each arm, you look at sort of the leading vertex, look at where it, which of these basis vectors it involves, and then you make some choices and throw everything into a class into one of these classes based on that. And then, well, you sort of then you prove this inequality for those, and sort of at that point, well, you sort of do some linear algebra, okay? And so looking at leading vertices on the arm. Gives these classes. So to return to our example here, right, when we were trying to embed this, we sort of looked at the central vertex. We had, so I guess I didn't say it, but in my notation here, the Poincare homology sphere is this guy here, where, and so when you look at this vector here, there are two elements appearing in the central vertex. In one of them, so in one of the classes we get this arm here, which is the one coming from 5 on 4. In the other one, we get 3 on 2, which is coming from this arm here. And then what you find now, we want to put 2 in one of these classes, but directly we found there was no way we could fit a vector of norm 2 in here pairing in the right way. And then if you go back to sort of this condition sort of stated in the theorem, this comes from bigger than 1. Bigger than 1. Okay. So I think that's all I want to say about that. Well, no, it's not. And so we'll notice that, for example, we couldn't get a vector of norm 2 in here, but if you want to, you can say, we could put a vector of norm 3 in here. And, that's allowed according to this theorem, since, 2 on 3 plus a third is, at most 1. Okay, so this is the sort of general criterion. So how does this sort of get us to a generalization of Neumann and Zagier? Well, let's just say, how does this get us to a proof of the Neumann and Zagier? Well, if this guy is a integer homology sphere, then, I told you how to compute the homology earlier. The order of the homology is the order of the exceptional fibers times this quantity epsilon y. Okay, and now if y satisfies the conclusion of this theorem here, then we can split this thing up as a sum. We split this as a sum over the sort of over our classes. Like this. Okay, you can write it as a sum over these classes, and, well, the point is that each of these summands here is at least 0, and, well, we must have, since this is non-zero, at least one of them must be, one of these quantities here must be non-zero, and so we get, say, well, let's say, you know, say at least one, say, you know, sort of relabel your classes if you want. Say C1 is such that, well, we have a strict inequality here, so you know, we get that this is less than 1, but this is a sum of rational numbers, so in fact we can say that this is, well, at most you know, it must differ from 1 by at least, you know, the product of all these denominators. Okay, and then when you sort of feed that back into here, this tells us that, well, you know, this quantity here is at least, well, the product of, you know, all of the fibers which are not in C1. And then, well, you find that if E is at least 2, then you have at least 2 classes, and you can't, you know, have all of these fibers in both of them. And so what you ultimately end up with is you find that this quantity is at least 4, which is, well, you know, a contradiction, since this number is not 1. Okay, it implies this is at least 4. I guess I should say if E is at least 2. And so, well, I guess what I should say is that this argument proves slightly more than Neumann and Zagier. It tells us that, well, you know, that if this guy bounds a negative definite manifold, well, then well, either E is 1 or the homology is at least 4. So somehow our theorem is 3 times better than theirs, since it works for 3 times as many sizes of homology. However, well, if you want to try a little bit harder, you find that, well, you can't actually sort of obstruct the homology being equal to 4, because there are examples of Seifert fibered spaces with sort of order 4 homology which bound rational homology balls. But it turns out that if you want to, you can actually sort of rule out negative definite manifolds for homology of order 5, 6, and 7 as well. But, and the arguments are of a sort of a similar sort of nature. start trying to fiddle things around into classes and sort of do some elementary number theory.
Claiming that this is, you classified all of the four manifolds among homology.
Oh no, definitely. The converse to this is definitely.
They didn't understand the fact.
Yes.
Oh, they did.
Yeah. So what they did was the R-invariant in its original form sort of comes as some complicated trigonometric sums, and what they showed was that that sum actually just evaluates to 2e minus 3, and then the obstruction to bounding a homology ball is this being positive, and so their theorem just follows from that.
Also implies that there's a distinction there. Does this also imply? I think that the d-invariance class of Seifert maybe just the homology. D-invariant obstruction is basically the same as Donaldson.
Yes.
So this tells you that the D and R obstruction and R-invariant are
I mean, you can get that anyway.
okay.
Well, I guess well. Sorry, no, this. Yeah, I mean, you don't need this to tell you that the R-invariant and the D-invariant give you different obstructions.
Yeah.
Exactly. You find your first example where you have E equals 1 and non-trivial, sort of non-diagonalizable intersection form. And on the topic of how much time do I have? Yeah, I mean on the topic of D-invariance, one corollary of this argument is to tell you that if you have a homology sphere with E not equal to 1, then the D-invariant is non-zero. And the proof of this is, well, proof of this comes in two parts. The one part is Elke's theorem, which tells you that the D-invariant of a lattice is 0 if and only if that unimodular lattice is diagonalizable, and then the second part comes from, well, I guess the D-invariant comes from Osvath and Szabo, but in particular, in this case, the observation comes from the D-invariant of this plumbing lattice determines the D-invariant of the Seifert fiber manifoldic band. So that piecing those two together tells you something about the D-invariance as well here. But yeah. Okay. So that was sort of, well, so now we have this theorem which, takes the obstructions from Donaldson's theorem and converts it into some sort of relatively neat sort of numerical condition. You might think, well, what else can you do with this? And so the second application I want to discuss of this is the question of which of these Seifert fibered spaces embed into, well, let's just say smoothly, as always, into S4. Okay, so sort of like the relevant historical background here is that, well, way back Hirsch and Wall, maybe 64, I think, well, showed that any three-manifold embeds into, well, into five-dimensional space. And so, you know, the natural question to then ask is, well, you know, which ones embed into S4? And then the question becomes a little bit, well, perhaps predictably, the answer to this question is some of them do and some of them don't. And well, you know, which ones do and which ones don't? Well, I guess the answer is most of them don't. And so the first obstruction you might, you know, come about to embedding things into S4 is, well, to observe that if Y is a three-manifold embeds into S4, okay, I guess, well, YA, right. And the first homology of Y sort of splits as a sort of sum of two isomorphic groups. And, well, proof of this observation, well, if you have a three-manifold Y inside S4, this cuts it into two pieces. We'll call U1 and U2. They're rational homology balls, it turns out. And then when you look at, you know, a piece of the Maya-Vittoris sequence, well, what you end up with is this. And then, well, these two, U1 and U2, are pieces of S4. So you can apply Alexander duality to get that, well, first homology of U2 is isomorphic to the second cohomology of U1. And then, well, we're assuming that this is a rational homology sphere, so universal coefficients tells you that this is just the same as this. Okay, and, well, so far this is you know, an entirely sort of, this isn't a smooth obstruction. This is a sort of topological obstruction. And when you apply it to, for example, you take Y to be a Seifert fiber space, when you compute its when you compute what its homology looks like, and you try and force it to, you know, split as a direct double, like this. So it embeds, yes, topologically. Well, into S4. Well, then it turns out that this homological condition forces you to take E at most n minus 1. This is a, I mean, you know, for example, this tells you that there are no doubly slice alternating Montesinos knots, which I'm sure is a fact known to someone somewhere, but I've not seen it written down anywhere. So this is a topological case, but, well, you know, these are irrational homology balls, so they're definite, and now we have a tool, you know, which applies in the, you know, in the smooth case. So, you know, you might ask, you know, do you get much more in the smooth case than the topological case here? And the answer is yes, and it's such an exciting answer that I always forget it. So. So in the smooth case, when you apply sort of, you know, this numerical condition here with, you know, this homological condition, well, if Y embeds smoothly, into S4, then, so Y again being a Seifert fibered space with all the, you know, all the previous conventions sort of in discussion, then, well, you get that rather than getting E at most n minus 1, we can more or less sort of cut that number in half, and then, well, with equality, so we don't just get this inequality, we can actually characterize the equality case with equality if and only if. Well, Y takes the form you get E minus 1 sets of P on P minus 1, and then, well, for the final set of arms, we get these invariants here, and so the inequality here, as I said, comes from sort of this condition here combined with this homological condition. But to actually characterize the equality case, you sort of actually have to get your hands dirty and sort of really understand some of these lattice embeddings and the sort of classification of the equality case. The equality case, I should mention, builds on work of Andrew Donald, who is an academic sibling of mine. And if you really want to, you can push this a little further. You can, rather than try and understand the equality case, you can try and understand the E equals sort of n on 2 case. And at this point, sort of everything, well, as E gets smaller, this problem gets rapidly more difficult. And in this case, you can draw up a sort of a conjectural list of things which you think would embed, and then obstruct half of them, embed the other half, and then, you don't know what to do with the third half. So, anyway, thank you. To pick the Poincare homology sphere, basically Friedman tells you it embeds. You take the topology. I would like more examples, sort of non-integer homology sphere examples. I'm not the best. I'm sure someone somewhere has them, but I'm not the best person to tell you about. That's a really good question. I've spent far too long thinking about it. So it's certainly it's a long way. I mean, the converse is certainly not true, even on a yeah. So what you might want to do, for example, is arrange of this, fix, just say, fix E equals 1, right? In this case, this condition is completely degenerate and just sort of tells you that epsilon is greater than or equal to 0. So what you might want to do then is take these and arrange all your Seifert fiber spaces in a rational simplex. And then when you draw, sort of pick which of these bound definite manifolds, color them one color and color everything else one color, what you find is sort of near the boundary of your simplex, so that epsilon is equal to 0 case, you get some kind of fractal-like picture. And then as you move closer and closer to the origin, move further and further from this line, it gets easier and easier to construct these manifolds, but it becomes quite complex. You end up with, this picture sort of gives you some kind of weird pyramid type setup, and it's really interesting. I'm not sure. I don't think they are. I think it's, I need to check, but I think it's, in this case, I think it's remarkable. It's more complex somehow. I mean, maybe there's some neat numerical characterization, but you can, there's nothing quite as clean. You can do crude things like where you take your more complicated plumbing and you sort of say, chop some bits off to convert it into this type. So you can get crude sort of things like that, but there's no really, that's not the right generalization, and I don't know what the right generalization is. And at this point, I should mention that there's a more general, Neumann and Zagier actually asked a more general question. They, in this theorem, they were sort of concerned with these star-shaped plumbings, but they asked the same question as if you have a definite plumbing which is unimodular and diagonalizable, then is it necessarily true that at least one vertex has weight 1? So we're sort of implicitly, we're answering that question in the star-shaped case. This sort of machinery gives you that, but more generally open.